Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about convolutional neural networks. Our idea is to look at convolutional neural networks under the signal processing perspective and compare it to filter banks. So let's get started. So far we used fully connected layers where the input is fully connected to each node in the following layer. Convolutional neural networks use a filter kernel instead, where each node is conducting a convolution like a filter. The filter kernel is also described as a receptive field of a certain size. At each position of this receptive field, an output is produced. Then it is shifted by a distance called stride, and a new output is produced, and so on. This has the advantage that the network is less dependent on the precise location of a signal to detect or recognize. There are convolution layers for 1, 2, and 3 dimensions. For the case of the MLfAS digit recognition, we will use a 2D convolution, and it's defined as this class here in PiTorch. And you can take a look at the documentation of the conv2D that applies a 2D convolution over an input signal composed of several input planes. Here, padding means zero padding at the ends of the signal, for instance, the boundary of our images. For padding equals to 0, only valid points are computed, which means that the kernel does not reach over the boundaries. For instance, if the kernel has a size of 3, we need a padding equals to 1 to obtain the same output size as the input. Here we implemented a convolutional neural network in PyTorch for the MLfAS digit recognition task. So we see here we have two 2D convolutional layers, and then we have a fully connected layer at the end. For the loss function, we again will take the cross entropy loss, and for the optimizer we use ADAM. When we look, we can compare the convolutional neural networks with the case of our fully connected network that we used before for the same MLfAS digit classification problem, and we will see that indeed we only have a fraction of the weights in our convolutional network when compared to the fully connected layer. This is an advantage for an implementation on smaller hardware. We can then train the convolutional network as before, and here we see a disadvantage. It takes much longer to train. We need over 1000 iterations or more to obtain a good solution, when compared to only about 10 iterations for the case when we use the fully connected network. So let's go through our model. Once again, we will import our Python packages and libraries. We are going to use PyTorch. We are going to use matplotlib to plot. Here we are defining the baseline model. So this is the convolutional neural network model that we are using: 2 conv2D layers, 1 fully connected layer. Then we have our activation functions. We are also using some max pooling. So what max pooling is doing is it's calculating the maximum or largest value in each patch of each feature map, and then the results are downsampled or pooled feature maps that highlight the most present feature in the patch. So not the average presence of the feature. In that case would be an average pooling, but you can take a look about max pooling also in PyTorch documentation. Then we are defining the batch sizes for our train, for test, the number of classes that we have. So basically it's the same procedure like we did previously, but now we just have a different model which is based on convolutional neural networks. Here we are loading our training set, we are loading our test set, and here we are just taking a look at some values just to make sure we loaded correctly, and we are plotting, for example, 4 images of the a data set, and we have here a 5, a 0, a 4, and a 1, and we have the labels 5, 0, 4, and 1, and we've done this previously, so there's no new things here. Then we also build our model. We use the cross entropy loss, we use the ADAM optimizer, and then we train our model, and after training we can save the trained weights, and then we can, for example, test, and then we have here this image that it's for me it's a 5, but the prediction here tells it's a 9, so it's a wrong prediction, but in this case it's not really clear a 5, so there is a margin for interpretations and errors. If we run this cell again, and now choosing a different sample from the test set, and now we see that this is a 9 and the prediction is also a 9, so this was a correct prediction.